Hey, I'm Nathan Super. This summer I worked with Avalanches and Entropy generation and sand timers. So forest fires, neuronal activity, biological evolution, these are all natural systems that display critical behavior without fine-tuning of parameters. This is a phenomenon known as self-organized criticality. It's indicated by power law distributions in event size and duration distributions. And that means that the events are scale invariant. Going forward, I'm going to be using a definition of avalanche that involves a minimum event threshold and power law statistics. And I looked at the system of an hourglass like this. It's a pretty simple system that previous work has shown to be a candidate for self-organized criticality. So questions moving forward. How does the way we observe this system affect whether or how we see avalanches? How does this affect the information content in our data, and can we relate the two? So our setup consists of an LED that sends light into a lens which focuses the light onto the object, which is the falling sand, sends the image through an objective which magnifies it onto the detector. We use an aperture as a field stop to allow varying amounts of the image to be seen, and we also use different orifices to change flow dynamics. So after magnification, the grain sizes are on the order of a millimeter, so I've given some dimensions here. So we're really interested in how does changing the aperture size affect our distributions. So our time series look like this. Like we have a second here. High signal would mean no sand is present, and so various amounts of sand are present over time. I have a distribution of voltages across a larger time scale. And for different situations, so different orifice sizes and aperture sizes, I've calculated the variance. We see a higher variance for small aperture and large orifice. In defining an event, I have to have a voltage threshold, which indicates a certain amount of sand in the being detected. So the duration of an event is the time spent under this threshold, and the size is the integrated voltage across that. So for one of the examples, these are the distributions for the various thresholds. I want to preface this by saying that we didn't see any differences across the different aperture sizes and orifice sizes. So that didn't show any differences. We don't really see much of a linear trend in the lower voltage thresholds, which correspond to a higher event threshold. Over maybe a half decade, there's some linearity, but I wouldn't call that a power law. We see more of a linear trend for the highest voltage threshold, but I would say, given a common sense definition of an avalanche, this isn't enough sand to qualify, so I would say we haven't seen any avalanches. Looking at the information content of our system, entropy is a quantification of the randomness of the system. We're interested in how much, depending on how much of the system we're viewing, how does that affect how much information we get from measurement. So we use the Cohen-Procacccia algorithm to calculate the entropy rate. This is a function of temporal and spatial resolution. It's a computationally inexpensive method. I provided the formula here for those of you who are interested, but basically it's the average value of information in a measurement for a given embedding dimension. And it's compared to a set amount of reference points that's less expensive than comparing all the sets. So in discretizing an analog signal, should have flipped this a while ago, but we have different temporal binning and voltage binning. So this continuous waveform gets turned into these points for this given binning. So we're interested in the entropy rate. So this is the difference, the amount of information present in one additional measurement. So how much do we learn from measuring, for gathering one more piece of data? So we can see for different observation areas, by that I mean aperture sizes, and for different orifice sizes, I provided the entropy rates for different voltage resolutions. And we can see that for the small aperture, we have a higher entropy rate than for the medium or the large aperture. And we can see that for the the large orifice, we have a higher entropy generation rate than for the small orifice, and this corresponds to what we saw for the variance. So I don't believe that we saw avalanches based on the event distributions. We didn't see the combination of a large enough minimum threshold and parallel statistics. Observation area and orifice size didn't affect our distributions, so we weren't able to establish a link with that in information content, but we did see higher variance and entropy generation rates for the large orifice and the smaller observation areas. So in the future, we could look at a different orifice to particle size ratio. The regime we were looking at, previous work has shown had a more constant flow, so we could look at a more fluctuating signal. And then we can move the vertical observation position along the hourglass neck in order to look at the flow at different heights before or after it's dispersed more.